Hello again, everybody. Today we're going to do some discussing about what it is that makes up atoms, what makes them different, what makes them similar, and then some of the radioactive decay that they might have going on too. So thing number one, before you even start this, you might want to pause the video and find yourself a periodic table. There's one in your agendas, or you can probably just find one online too if you're looking for that. But a periodic table will definitely come in handy here. So thing number one, what makes up an atom? Well, atoms are made of protons and neutrons and electrons, but to give a little more words that go along with it, the first thing is a nucleon, and those are just protons and neutrons, are the things that are in the nucleus. So nucleon is just a fancy word for the stuff that's in the nucleus. Other important terms would be the atomic number and the mass number. The atomic number is just simply the number of protons that you have in a nucleus. And if you look on your periodic table, you'll see that on the periodic table, the atoms grow by increasing atomic number. Like hydrogen has atomic number 1, helium has atomic number 2, and so forth. The mass number, it's the protons plus the neutrons. That you don't exactly find on your periodic table. That's something that you just have to be able to do some figuring out. The number that's on your periodic table that you might see is your average atomic mass, and that's the decimal number that shows up on your periodic table. Like carbon is 12.01. That is what we call the average atomic mass. Some other things about the atoms is you can have different types of isotopes, right? So an isotope, it's the same atom, so you have the same number of protons, but you'd end up having different number of neutrons. And really with isotopes, they react exactly the same way. They have the same type of properties there, but their masses are the things that are going to be different. What we measure isotopes in would be the AMUs, and those are the things that are on your periodic table. As you look at the average atomic mass, it takes into account all the different isotopes that might exist for an element, and it takes those into account. So the isotopes are measured in something called AMUs, which are abbreviated just AMUs. What is an AMU, you ask? Well, I thought you probably would, right? And that's basically the mass of the 1/12 the mass of a carbon-12 atom, which is really just basically the mass of a proton. So that's really what an AMU is. So when we talk about different types of isotopes, I'm going to talk about that first before we get to the stability. Here you actually have 3 different isotopes of hydrogen, right? So you got hydrogen, and we call this one hydrogen 1. This will be called hydrogen 2, and this will be called hydrogen 3. They do have fancy names, protinium and deuterium and tritium, but they're really just the exact same type of hydrogen atom in the case that they would react the same, but they have different masses. So again, when you think about an isotope, it's the same atoms, they react in the same way, but they have different number of neutrons, so they have different masses. And one thing that's kind of unique here when you talk about the stability of different atoms, with little atoms, the smaller they are, the more you're going to have a ratio of protons and neutrons that are going to be equal. The bigger an atom gets, the less stable it's going to get if it has the same number of protons and neutrons. Generally, as they get bigger, atoms are going to be more stable when there's more neutrons than there are protons. So you can kind of check that out if you look at some bigger elements here. But if you think about putting all these different isotopes together, all these hydrogen isotopes together, and you average them out, if you look on your periodic table, you see that the average mass of hydrogen is actually 1.01. So that tells you that the majority of the hydrogen on the planet is going to be hydrogen that has a mass number of 1. So as far as stability goes and radioactivity, that's one of the ways that we look at how stable a given element is. So what happens is there's a lot of elements that actually undergo radioactive decay, which means they break apart or they turn into other things. And when that happens, that's what's known as radioactivity. So sometimes you confuse radioactivity with radiation. Like we can have electromagnetic radiation like we talked about in the past. But here we're actually talking about stuff that's going to undergo decay. So the radioactivity we're going to talk about here would be things where we get alpha particles, beta particles, positrons, and gamma rays that are actually going to do some different types of radioactive decay. Radioactive decay isn't all that uncommon, although you might think about it as something that doesn't occur all that often, but it's probably happening inside of you right now. So radioactivity is one of those important concepts for us to understand. So the first two to talk about would be alpha particles and beta particles. You can see the symbols there. But essentially an alpha particle is just a helium nucleus. So there's some really big isotopes that when they undergo radioactive decay, they give off alpha particles. They're going to be giving off a helium nucleus. So a helium nucleus is 2 protons and 2 neutrons. That's why. So the symbol for it is this. Essentially, that's what's going to be given off of there. Alpha particles, they do give off radiation, although they're not very penetrating types of radiation. A couple pieces of paper will actually stop alpha particles. That doesn't mean they're not dangerous, because when substances give off alpha particles as part of their decay process, it can be a very dangerous type of radiation. But you actually have to inhale it or take it in through your mouth to actually get the radiation inside of you. So generally, alpha particles aren't considered real dangerous types of radiation, just because your skin is actually enough to stop the alpha particles. A beta particle is essentially just electrons coming out of the nucleus. So when something undergoes a beta decay, you actually get a neutron that's going to be turning into a proton, which is kind of unique, and then an electron is given off out of that too. So there's your symbol right there for a beta particle. Give a little bit more information on that in a second here. Positrons and gamma particles or gamma rays are another type of radiation. Positron, which might sound like something on Transformers, it's not. It's just basically an anti-electron, like it says there. It has the same mass as an electron, but it has the opposite charge. So sometimes people think that stuff like that can't exist, but it really does. There are anti-electrons. Sometimes, think about it as antimatter, if you've ever heard of that. But that's really what a positron is. It's a type of antimatter. And then the other one would be gamma rays. Those are things that are actually really, really dangerous to humans, because they do have so much energy. Essentially, they're high energy photons, so it's not a type of light. But if you remember on the electromagnetic spectrum, it was the stuff that had the smallest frequency. I'm sorry, the smallest wavelength, but the highest frequency. And therefore, it had the highest energy. Gamma rays can actually go through small amounts of lead. Unlike the positrons above, they're going to be stopped by a little bit of aluminum, just like the beta particles did. I forgot to talk about that. Like it says here, a few millimeters of aluminum. The same would be true for positrons also. A little bit more on the way we would look at the way they're going to be expressed. So alpha particles, helium 4/2. Beta particles, you can write like this one right here. So these are what we call beta negative ones, actually. So you got a 0/-1. Oops, should make that bigger. Alpha particles, 4/2, so you got 2 protons and 2 neutrons. That's what gives you the 4. The beta particles, these are actually called beta negatives, and we'll talk about those in a second here. But they don't have a mass. But you remember down here is going to be -1. For beta pluses, you got 0 on top and 1 here. And then gammas just have a symbol like that, where we're just going to be having the change from basically high energy photons that are going to be coming out of the nucleus. So if we want to look at a little bit of how this decay actually takes place here, we're going to say we got some francium-211, which means that the mass of it is 211. We want to know what the products would be. The second one we're going to try would be an alpha decay. So it's going to say you have an alpha particle with an atom of iridium-181 that's going to come out of it, and we want to know what we would be starting with. So if you want to pause the video for just a second just to write down what's there, we're going to go ahead and work that out on the board here. So we have the francium. So it's francium-211. That means it's going to have a mass number of 211. 87, that's the atomic number of francium. And it says it's going to happen by an alpha decay. So it means we're going to have to put a helium, 4/2. That's a symbol for an alpha particle, which I'm getting from right here. And what we need to do is make sure that our numbers all add up. So what our total information is over here, that's what we have to have on the other side too. So if we got a 4 and a 2, well, we'd have to take a 4 and a 2 away from here. So instead of being 87, this one over here is going to be 85. And if you look up 85 on your periodic table, you're going to see that 85 is going to be astatine. So we put AT right there. And then up on top, since we got 211 and we take away 4, whoops, I'll make that 207. Right, so it'd be what we'd call astatine 207. Down here, we have iridium as one of our products. Then we also have an alpha particle being given off here. Well, here we got 77 and 2. That means our number would be 79. 181 and 4 would be 185. So you have to look that up on your periodic table. And that would end up being some gold. All right, so you would call that gold 185. All right, so those would be the two reactions that would happen with the radioactive decay. So you're going to have francium undergoing a decay, giving off an alpha particle, you're going to have some gold undergoing decay, giving off an alpha particle. So when atoms actually decay, when they undergo radioactive decay, there's actually particles that are going to be coming out of them, and they turn into a different type of an element. So beta decay, a little bit more information for that one. There's actually two types, like we talked about. There's beta minus and beta plus. Beta minus would be the first one that we talked about, just a regular beta particle, where essentially you have a neutron turns into a proton. Beta plus would be where you have a positron being given off there, and basically a proton gets turned into a neutron. So there's two different types of beta decay that takes place, but you can really think about them as being a beta particle or the positron. So. Here we go, on the top we have our beta minus. Essentially you got carbon-14 turning into nitrogen-14. All right, so what's happening there is you're essentially getting one less neutron, so you're going from 8 to 7 neutrons, or you can think about it as you're getting one more proton, right, going from 6 up to 7. Then down here, if you got beta plus, like we said, we're going to be ending up getting a neutron, so you're going from 4 to 5 neutrons, and then your protons are going from 6 to 5. Okay. You don't really have to worry too much about the neutrino and antineutrinos. That's not what we're really worrying about right now. The biggest idea is that this one right here would be a beta plus, which is really just your electron coming out of it, or your beta minus, which would be your beta particle or electron. And this one here, your positron, would then be the essentially the antineutrino or the positron that's coming out of it. All right, so here we're going to take carbon-14. We'll say in this particular case it's going to undergo a beta plus decay. And the other one we're going to have a magnesium-23 undergoing a beta minus decay, and we want to think about the products that are going to be there. So I'm going to do this on the board, make this a little bit bigger, and do some erasing. All right, so here we go with our reaction. So the first one, we're going to have a carbon-14 doing a little different decay. We know that it's going to undergo a beta plus decay. So that means that we can pick our beta plus particle, or a positron. So we've got a 0 and a 1. Now we can just think about adding up masses that are going to be there, right? So the total mass of this needs to come up to what this one is at the beginning plus this one. So if this is 14 and this is 0, that means by default that one's going to have to be 14. And if this is 6 and this is 1, well, to get up to 6 on this side, we'd have to have a 5. So 5 and 1 gives us 6, just like over here, and 14 and 0 gives us 14, like that one. If we look on our periodic table, you'll see that the fifth element is going to be a boron. So that would be that it says that if a carbon-14 undergoes a beta plus decay, it's going to give us boron-14. The bottom one, we know that our particle is going to be magnesium-23 with a beta minus decay. So we think about just adding up particles again. Well, 23 and 0 is 23, and 12 and negative 1 is 11. Well, that would have to be sodium. So that would tell us that if we're having a sodium 11 or a sodium 23 that's going to undergo a beta decay, it would give us the magnesium right there. Okay? So in doing these, really just look at the reactions that are there, look at what kind of particles are going to be present. So then we got to talk about how these things actually decay. The rate at which they decay is something called the activity. It can be measured a lot of ways. One way is to measure it in becquerels, which is kind of a funny thing to say, but it's really just one decay every second. So 1 becquerel would be 1 atom decaying every second. Another unit for that would be the Curie, which is 3.7 times 10 to the 10th, probably a more realistic measurement because it actually measures when you have lots and lots of things that are actually going to be decaying. It was named after Pierre and Marie Curie that discovered radium, so it's kind of a nod to them in the naming of the unit. Last thing we're going to be talking about a half-life, and that's just the amount of time it takes for half of something to go away. Radioactive things are always measured in half-lives. Some things have very, very short half-lives, and some things have very, very long half-lives. There's an equation for figuring out how much of something is going to remain. I really don't care that you know that. If you just do a little bit of reasoning, you can probably figure out your half-life information too. So we're going to make, next screen, we'll see this one a little bit bigger to do some thinking there. So here would be the same image, a little bit bigger. It says percent of substance remaining. So if we have 100% of it remaining, we're going to go down to eventually getting basically down to 0. And you can see that we're going through half-life. So here, we went from 100% to 50%. Well, that means we went through 1 half-life in 1 unit of time, whatever that was. Then we went from 50% to 25%. Well, we did that another unit of time. Then we went from 25% to here would probably be about 12.5% in 1 more unit of time. So on your guided notes, what I would like you to figure out is what would be the half-life of this particular graph right here. Okay? Again, if you have any questions, please let me know. Hope you have a good day.